1. Based on your answers of exercise 3, I think it's necessary to explain some terms, functional dependencies, keys, and superkeys. Okay, now let's discuss these terms. Firstly, functional dependencies. Let's look at this definition of functional dependencies. X functional dependency A is assertion about a relation R that whenever two tuples of R agree on all the attributes of X, then they must also agree on the attribute A. Then we see X functionally determine A, or A functionally determine A holds on R. Okay, based on this definition, we can find the three cases of assertion functional dependencies. Let's take this relation for example. The first case, if any two tuples with the same values in their A components also have the same values in B, then A functionally determine B holds. Look at these tuples. Okay, now we can find, let's check if A functionally determines C. Does A functionally determine C hold? If we want assert this FD, we'll check the components on A, and we found this one and this one. They are with these two tuples have the same values A1 in A, and they also have the same values on C. And these two tuples, they have same values in A, and they also have same value on C. Okay, we can find, if we check all the tuples in this relation, we found if any two in these relations, any two tuples with same value in A also have the same value in C, then we see A functionally determines C holds. But if we find in this relation there are two tuples with the same values in A does not have the same value in B, then A functionally determine B does not hold. Okay, still this relation. Let's assert the FD C functionally determine A. And check the component on C. We find these two tuples with same value in C, and they also have same value in A. But we find these two values. They have same value C2 in C, but the value in A are different, A2 and A3. Now we can find two tuples with same value in C does not have same value in A. Then C functionally determine A does not hold. Okay, it exists. And here is anyone. Okay. Okay, now let's check this one. A, B functionally determine D. If A, B functionally determine D holds in this relation, let's check B and C. Okay, now we can find these two. They have same value in both B and C. But they have different value on D. So BC functional determine D does not hold in this relation. And there is another case of asserting functional dependencies. If any two tuples haven't the same value in their A component, then A functional determinant holds. Okay, let's look at this. The components on D. And we cannot find any two tuples with same value on D. D1, D2, D3, D4, D5. We can't find any two tuples with same value on D. Then D functional determine A, D functional determine B, D functional determine C, D functional determine D. All these FDs hold in this relation. Hold in this relation. And because if we cannot find any two tuples with same value in D, then D functional determine any attribute holds in this relation. So A functional determine A, D functional determine A, D functional determine B, D functional determine C, all these holds because we cannot find any tuples with same value. Okay, this is the three cases of assertion. In the former example, we did assert a functionally determined based on the sample. But in fact, we cannot just assert FD based on a sample because the sample, the tuples in sample may be changed. So we must assert the FD based on all possible tuples. Let's take a look at this example. In this example is an example in our book. And if you want, you can read this part in page 69 in our book. And now, firstly, let me introduce the meaning of these attributes in this relation. Title, the title of the movies, of the movie. Year, the year of the movie, produced. The length of the movie, genre of the movie, such as science, genre, comedy, cartoon, and so on. Studio name. Studio name is the name of the studio who owns this movie. And in this book, it is supposed that a book can be owned by only one studio. And star name, the name of the stars who act in this movie. And there are maybe more than one stars who act in this movie. Okay, and for a movie, there is only one dance, one genre, one studio. And there are maybe more than one star acting in a movie. Okay, these are the attributes of these relation movies. Now, and this is the sample. This is a sample. This is a sample. Okay, based on this sample, title functionally determine length, genre, studio name, hold. If we just look at this sample, we'll find any two tuples. If any two tuples with same value in title, then they have same value in length and genre, studio name. Maybe you will tell me, okay, it holds in this movie. But, but, but this but if we look at this sample carefully, maybe you can find this sample is not it not in that does not include all possible situation or possible cases. Let's look at these two tuples. Look at these two cases. Mulan. Mulan is a movie, and in 1998, Disney produced this movie, Mulan, and this is a cartoon. This is a cartoon, and in this movie, Ming Nan Wen is one of the star in this movie. And in this year, Mulan is reproduced by Disney. Reproduced by Disney, and now it's an action movie. And in this movie, Yi Fei Liu, sorry, Yi Fei Liu is one of the star who act in this movie. Okay, now these are two different movies with same title, same title. So based on these two topic, we know there are maybe there are two movies with same title, but they have different lengths, different genre, maybe different studio name. So based on or possible sample, not just based on one sample or possible sample, we can find this FD does not hold because title cannot identify a movie. A title cannot identify a movie. A movie, there is only one dance, one genre, one studio for a movie. But title cannot identify a movie. Then it means if there are two tuples with same value in title, this tuple may be not mean a same movie. Then they may have different value on length, genre, studio name. So this this FD does not hold in the movie. In these relation movies. And in our book, it's supposed that in 1 year in 1 year, there it, there if two movies have same value and produced in 1 year, then this is the same value, same movie, same movie. Then based on this suppose, title year can identify a movie. can identify a movie. Then title year, if any two tuples with same value on title and year, then it these two tuple is these two tuples are about one same movie. Then they have same title, dance, same genre, same studio. So that means if any two tuples with same value on title and year, then they will have same value on dance, then on genre and studio. Then this means so we say title year functionally determine dance genre studio name holds in this relation movies. Okay, now title year functionally determine star name. Does it hold? Now let's look at this one. These two tuples have same value on title and year, but they have different value on star name. So based on these tuples, based on this sample, we can find the two tuples with same value on title year, but they don't have same value on star name. So this FD does not hold. Okay, now let's check it based on or possible, based on the semantic or the meaning of this attribute. If any two tuples with same value on title year, then it means these tuples are about same movie. But in a movie, there are maybe more than one type star acting in this movie. So a movie, there are maybe more than there are maybe there are more than one stars in a movie. So if any two tuples with same value on title year, does not means that they have same value on star name. So not it does not hold. Okay. Star name functional determine title. Does it hold? Well, based on this tuple, based on these tuples, based on this sample, we cannot find any tuples with same value on star name. From the former, based on the former example, we can see star name functional determine title. Is right? No, because in this sample we are consider if we want to assert an FD, we must consider all possible tuple. We know, for example, Vivian Lee. Waterloo Bridge is a very famous movie, and is Vivian Lee is acted. Vivian Lee acted in this movie. So, if we add this movie in this relation, we can find two movies, Gone with the Wind, Waterloo Bridge. Bridge, these two movies, the information of these two movies in this relation, and we can find then we can find two tuples with same value on star name, Vivian Lee, but they don't have same value on title or movies or dance or genre or studio name. So, based on all possible tuples, this relation, this FD does not hold. Does not hold. Okay, now we know we cannot assert FDs in a relation just based on one sample. it's necessary to assert it based on all possible tuples, and all possible tuples are designed in our mind, our mind, based on the database requirement and the meaning of the attributes. Okay, now let's consider this example based on the meaning of the attribute. Okay, this is a relation student. A student ID is an ID or is ID of the student, and a student ID can identify a student. Name is name of the student, gender of the student, the ID of the department where the student will study in, course ID, the ID of the course, what the student is studying, and course name, the name of the course. Score is the score is the score the student get in this course. For example, if there is a tuple like this, okay, S001, John, male, 6, C002, for example, database. Okay, database system, and the last one. Okay, if this is a sample in this relation, it means then this is the student ID. ID and student ID will identify only one student, and the name John is the name of the student. He is a boy, and he work in the he studies in the department 6. 6 is the ID of the department, and the department ID identify a department. And C002 is one score, is one course, which S110 is starting. And database system is the name of C003. Course ID identify each course. And 80 is the score S001 got in database systems in this course. Okay, now let's before we assert the FDs in this relation, I'll tell you some facts, the database requirement, some requirements. Student ID identify each student. A student have only one name, one gender, and one department. A department ID identify each department, and a student may land more than one course, and yeah, a student may land more than one course, and course ID identify each course, and name. For a course there is only one name, and a student can get only one score in a course. in a course. Okay, based on the requirement. Based on this requirement, let's assert this as this. Does student ID functional determine name, gender hold? Okay, then let's consider it. If any two tuples with same value on student ID, then these two tuples are about this same student. And in the requirement, I said a student have only one name, one gender. So they must have same value. These two tuples about one student must have the same value on name and gender. So it holds. So it holds. Name functionally determine gender. In your exercise, someone told me, we cannot find any two person with same name. But in China, there are some meanings of Li Qiang, meanings of Zhang Hong, meanings of meanings of Zhang Wei in China. We often find two different person with same name. So in China, name cannot identify a student. Name cannot identify a person. And even a boy, maybe we can find a boy and a girl with same name. So in China, and we can say if any two students with same name, then they have same gender. No, we cannot say that. So name functionally determine gender does not hold in China. Okay. And student ID functional determine score. Score is the student gets in this course. And we know a student may enrolled in may land more than one scores. He can land 3, 4, even some hundreds of course. So we in each course he will get a score. So for a student, there are maybe more than one score. Student ID identifies student. If any two tuples with same value on student ID, then these two tuples is about the same student. But they may these two tuples may be about different course. So they will have different value on score. So student ID functionally determines score does not hold based on our requirement. In the requirement, the student may land many courses. Okay, next one. Student functional determine course ID? No, because the student may land more than one course. Okay, and student ID, course ID functional determines score. And in the requirement, I said a student have only one score in one course. And if there are two tuples with same value on student ID and course ID, then it means these two tuples is about the same student in same tuple. They can got only one score, so the values on score are same. Must be same. So student ID, course ID, functional determine course holds. When we judge if a relation is a good design, asserting FDs in this relation is the first step. And then we'll find all the keys, super keys in the relations so that we can determine the normal form of the relation so that we can judge the if the relation is good. And there are many ways to find the keys and the super keys. The easiest way is the closure. Closure is one of the rules about functional determinants. And there are some important rules about functional dependencies. And based on these rules, we can find all the FDs in a relation based on some FDs. And let's review these rules. Splitting, combining rules. If we can find if there is a functional determine B, a functional determine C in a relation, then based on this rule we can get a functional determine BC. Is combining rules. Then if there are two FDs with same have same left side, then we can combine the right side, and we can also split the right side. Split right side. If a functional determine B C in a relation, then we can get a functional determine B, a functional determine C. Okay, it's splitting combining rule. And trivial dependency rule. What is trivial dependency rule? If we write the if we know a functional determine like this, a functional determine a b functionally determining BC. Okay, if we do get a v functionally determine BC, we can delete the attributes appears in the from the right side appearing in the left side, B appearing in the left side. So we can delete it, or we can add, and we can add an attribute appearing in the left side to the right side. If we have a b functional determine C, then we can add a in the right side. Then we can get a b functional determine AC. And we can also get a b functional determine add b in the right side, BC. And we can also delete the right attributes appearing in the left side from the right side. Okay. This is trivial dependency rules, and this in these rules we must know what is trivial dependencies. Completely trivial dependencies, because only completely trivial completely untrivial dependencies is important in in the BCNF, in the definition of BCNF. What is completely non-trivial dependencies is that this is an and this is an this is a completely non-trivial dependencies, and in this FD we cannot find any attributes appearing in both left side and right side. So this is a completely non-trivial dependencies, but is not but this is not a completely non-trivial dependencies because we can find A appearing in both left side and right side, so it's not a completely non-trivial dependency. Okay, and we'll use this concept. This concept completely non-trivial dependency in the normal form, BC normal form, in the definition of BC normal form, and transitive rules. What is transitive rules? If we can get A functional determine B functional determine C, if these two FDs hold in the relation, then we can get A functional determine C. We can get this one. This is trivial. A, B, B, C, then we can get A functional determine C. And there are also and Armstrong's actions is also very important to rules. But now, in this time, I want to discuss the easiest way to find all functional determinants, the closure of attributes. I think this is the easiest way. So if we when if I was required to find keys, super keys, or or find or possible FDs based on some FDs, I will choose this way. Why I will choose this way? I will choose to compute the closure of attributes. And what is closure of attributes? Closure of attributes. A closure of attributes is the set of the attributes such that every relation that satisfies all the FDs in set S also satisfies the A1, A2, AN functional determinant B. That is A1, A2, AN functional determinant B follows from the FD functionary FDs of S. This is a closure of attributes, and we denote the closure of attributes by the subscript plus. And A1, A2, AN is always in the closure of A1, A2, AN. If A1, A2, AN functional determine X, then X must be in the B. In the closure of A1, A2. Okay, now how to compute the closure of attributes? An easier way to test is to compute the closure of Y. The basis why the closure of Y is Y, because Y must be in the closure of Y. We know Y functional determine Y. Y functional determine Y is always be true. Is always true. Is always true. And because if there are any two tuples with same value on Y, must be same on value on Y. So Y functional determine Y. Then so Y must be in the closure. Then this Y is the basis. And then we look for each FD's left side, if the FD is left side. If the left side X is a subset of current closure Y, then A, the right side A, left side X in the subset, then A add A to Y, then A is added. We'll get new y closure, a closure of y, and repeat these steps so until no new until no new no new attributes can be added in the closure. For example, okay, as now, based on this relation and a set of let's compute AB, the closure of AB. The closure of AB, okay, now let's compute it. AB, the closure of AB, so that's the let's compute it based on the basis AB. AB must in the AB, or must in the closure of AB. Then AB, let's look at each FDs. BC functional determine AD. BC is not the closure, or is not a subset, of current closure. BC is not a subset of AB, so skip it. D functional determine E. D is not a subset. CF functional determine B. CF is not a subset. Now AB. AB functionally determines C. AB is a subset of AB, of current closure. So we'll add the attributes on the right side, in the right side to the closure. C is added. And then check again. Now, because if we check again, maybe we can add more new attributes. Check again. Now BC. Okay, because BC is added, C already been added in this closure. So now BC is a subset of this closure. BC, we can find BC here. So we'll add AD in it. A already in the closure. Now we'll get D. Then D is a subset of this closure now. Then we add E. CF, no, CF is not a subset of current closure. Check again. No. Now we cannot find any attributes can be added in the closure. So AB, the closure of AB is A, B, C, D. Then it means AB functionally determine A, B, C, D, E. If we use splitting rules, we can get AB functionally determine C, AB functionally determine E, and AB functionally determine D, E, A, C, D, E. And we can there are six attributes in R, but while F is not in the closure, then this means AB functionally determine E does not hold. Okay, this is an example of computing the closure of attributes. And if we find the closure of an attribute, then it means this attribute, the closure can be in the right side of an FD. And if an attribute is not in the closure, then it means this attribute functional determine this attribute does not hold. Okay, And based on by computing closure, we can test. Then we can test whether FD follow from a set of FDs. Let's look at this example. Let us consider a relation with schema R, A, B, C, D, E, F, and set of functionally dependencies. AB functional determine C, B, C functional determine A, D functional determine E, C, F functional determine B. Okay, if A, B functionally determine D hold, holds, or if A, B functional determine B follow from S. Now, if we want to check this, test this, we can compute the closure of AB. The closure of AB, the basis AB. Now let's look at each FDs in S. Each FD in S. A, B functional determine C. A, B is a subset, so we add C here. B, C functional determine A, D. Okay, we can find B, C here. So let's add D. D functional determine E. E already in the current closure, so E is added. Now CF. Oh, we cannot find CF here. And check again. No new attribute can be added. Then we can get the closure of AB is A, B, C, D, E. A, B, C, D, E. So D, then we can find D is in the closure. Then A, B functionally determine D follows from S. Follows from S. And if we want to test if we want to test D functionally determine A, then we can compute the closure of D. The closure of D, the base is D. AB is not the subset. BC is not a subset. D, okay, D is a subset of current closure. Then we can add the right side E here. CF, no, we cannot use this FD. Try again. No new attribute can be added. Then D, then DE is the closure of D. And we cannot find A. We cannot find A. So D functional determine A does not hold. Does not hold. Or D functional determine A does not follow from S. Okay, now let's discuss key and superkey. What is key? We say a set of one or more attributes A1, A2, An is a key for a relation if those attributes functionally determine all other attributes of relation. And no proper subset of A1, A2, An functionally determine all other attributes of R. And this condition is also a definition of superkey. And this is another condition of key. So we know key is a minimal superkey. From the definition, we know a key is a minimal superkey. And then what is a superkey? A superkey is a superset of a key, a set of attributes that contains a key, and a superkey is a set of those attributes functionally determining all other attributes of relation. So from the definition of key and superkeys, we can find the relation between keys and superkeys. All keys are superkeys because a key is a minimal superkey. So a key is a superkey. So all keys are superkeys. And some superkeys are not keys. What is a key? A minimal superkey is a key. And if a superkey who's not the minimal, so then the superkey is not a key. And based on the definition and the closure and the definition of key and superkey and the definition of closure, we can find the relationship between closures and keys. If a set of attributes, the closure of this set is a set of all attributes if and only if A1, A2, An is a superset of for the relation. It means that if there is a R A, B, C, D, then if A, the closure of A is ABCD, then we can see A is a superkey. Then A is because the closure of A is ABCD, and if ABCD and ABCD are the set of or is the set of all attributes of R. Then then A is a superkey, and because A has in A is has only one attribute, so it must be minimal. So A must be a minimal superkey. Then A is also a key. Now A is a key and a superkey. And a superkey. Okay, and now A, the closure of A is ABCD. Then the closure of AB, the closure of AC, the closure of AD, the closure of ABC, the closure of ABD, the closure of ACD, the closure of ABCD. All the sets including A, the closure of these sets is ABCD. Is ABCD because A functionally determine ABCD. Then AB functionally determine ABCD and others. So we can get this. Then, and from this, we know AB, AC, AD, ABC, ABD, ACD, ABCD are superkeys. What is superkey? A superkey is a superset of a key. A is a key, and all these are supersets of A. Then these are superkeys. Okay, this is the key superkey and how to find a superkey by closure. Now let's look at this example. We already discussed these relation movies. Title, year, length, genre, sorry. Genre, studio name, star name. And from the the former discuss, we know title, year, functionally determine length, genre, studio name. Studio name. But title, year, functionally determined star name does not hold. Does not hold, because if any two tuples with same value on title year, it means these two values is about a movie. But there may be more than one stars in a movie, so the star name may be different. So we cannot assume the value of these two tuples be same. So this FD does not hold. And based on this, if title year is a key, is title year a key? Then we can based on this FD compute the closure of title year. The closure of title year base is title year. And because title year functional determine length genre studio name, so length genre studio name are added, and we cannot find others. So the closure of title year is title year length film type, the genre studio name, no star name in the closure. So title year is not a key. How about title year star name? Okay, now we can compute the closure of title year star name. And now we can find the base is title year star name. And then because title year functional determine genre, length studio name, so length genre studio name are included. Then we can find the closure of title year star name is the set of all attributes. So title year star name is a key. Okay. And why? Based on this, we know if a set the closure of a set is a set of all attributes, it means that this set is a super key. Why is this a key? And because if we delete anyone off from the set, the closure of the set is not the set of all attributes. So it's a minimal super key, so title year star name is a key. Now, can we find the super key? We already know title year length is the key and is the only key. We cannot find other keys. How about the super key? Okay, all the supersets of the key are super keys. Then supersets. Title year is a superset. Sample title year star name is a super key. It is a key and it is also a super key. Okay, title year star name. Okay, length. We can add one. And genre or and we can add studio name here. and add length gear, and so on, and so on. This is they are super keys of the relation movies. They are all superset of the key title year star name. Okay, now do you know what is key and what is super key? From your exercise, the answer of your exercise, I found most of you didn't know what the concept, the definition of super key. Don't know the relationship between keys and super keys. And if A functionally determine B holding R and C, so can you find the key of R? The keys of R? Oh, if there is only one attribute, only one FD. If there is only one FD, R A functionally determine B hold in a relation R ABC, then the key is AC. The key is AC. You can compute the AC, the closure of AC, the closure of AC, the base is AC, and because A functional determine B, A is the subset of the current closure, so B is added. So B is added, then ABC, ABC are all the attributes of R. So AB, so AC is the key of. Now, based on the definition of FD, how to compute the closure of FD, or a closure of a set of attributes, and the definition of key and super keys. Let's look at this example. Consider a relation with schema R, A, B, C, D, and functionally dependencies A, B functionally determine C, C functionally determine C, and D functionally determine A. What are all the non-trivial? Here, non-trivial is completely non-trivial. All the completely non-trivial functionally dependencies that follow from the given FDs. Okay, if we want to find all the FDs, we can compute the closure of all combination of attributes. ABCD, there are 4 attributes, so we can find this combination of attributes A, B, C, D, AB, AC, AD, BC, sorry, matter. BC, BD, and AC, BC, BD, CD, ABC, ABD, ACD, BCD, and ABCD. Okay, now I've listed all the possible combination of ABCD. Now let's compute the closure of each combination. The closure of A, the base is A. AB, no, it's not a subset. C is not a subset. D is not a subset, so the closure of A is A. Now closure of B. The base is B. We cannot use any of them. So the closure of B is B. Now C. C, oh, can find this one. C functionally determine D, so D is added. D functionally determine A. Now A is also added. Okay, we can find B cannot be added. Now, from this one, we can get C functionally determine D and C functionally determine A. Now, please don't write C functionally determine C because C functionally determine C is not a completely non-trivial FD. It's a it's an FD, and this FD must be heard, but it is not a completely non-trivial dependency. Okay, now the closure of D. The base is D, and A can be added. No others. No others. So D functional determine A is also an non-trivial dependencies follows from the given FD. Now closure of AB. Closure of AB, the base is AB, and because AB functional determines C, AB is a subset, so C is added. And because C functionally determine D, so D is also added. Now we can find the closure of AB is ABCD. And then we can get the closure of AB functional determine C and AB functional determine D. And from this one, we can find AB is, the closure of AB is the set of all attributes. So AB is a super key. And because the closure of A is not a super key, and the closure of B is also not a super key. So AB is a minimal super key. So AB is a key. Now we can find AB. This is a key. Now let's compute the closure of AC. The base is AC. ACC functionally determine B. Okay, D is added. No others. So AC functionally determine D. Okay, now let's compute AD. The closure of AD, the base is AD. D, okay, it's AD. And the closure of BC. BC, the base is BC, and because C functionality determine D, D is added, and because D and functionality determine A is added, A, B, C, D. And now we can get B functionally determine BC functionally determine A, and BC functionally determine D. And BC is also a super key. And BC is a minimal super key because the closure of B and the closure of C are not are not a set of all attributes. So BC is also a key. Now the closure of BD. The BC is BD. D functional determine A is added, and AB functional determine C, so C is also added. And we'll get BD functional determine A and BD functional determine C, and BC is also a key. And BC is also a key. Now we already find 3 keys. A, B, B, C, B, D. Go on. CD, the closure of a CD. The base is CD, D functional determine A, so A added, but we cannot find B. So CD functionally determine A, we can get this FD, but CD is not a super key. Okay, now closure of BC, and because AB is a subset of BC, and AB is a key, so ABC is a super key of a superset of a key, so ABC must be a super key. It is a super key, and now ABCD is the closure of ABD. ABCD is a super key, but it is not a key. But it is not a key because AB is a key. BC is a key. BCAB is a proper subset of ABC. And they are proper subsets of ABC. So ABC is not a minimal it's not a minimal super key. So it's just a key, but it's not. It's a super key, but it's not a key. And ABC ABD is also a super key. BCD is also a super key, but they are not keys. ABCD, the closure of ACD is ACD. So we can get this FD completely non-trivial FDs. ABC functionally determine D, ABD functionally determine C, and BCD functionally determine A. And the closure of ABCD must be ABCD. So ABCD is also a super key, and the set of all attributes must be a super key. A set of all attributes must be a super key. Okay, now we can find what are all non-trivial completed what are non-trivial FD that follows from given dependencies? C functional determine D, C functional determine A, D functional determine A, AB functional determine C, AD functional determine D, and so on. All these I've already listed in here. Okay, what are all the keys? There are 3 keys. We can find 3 keys: AB, BC, and BD. And what are all the super keys for that are not keys? Okay, these A, B, B, C, B, D, A, B, C, A, B, D, B, C, D, A, B, C, D are super keys. But these 3 are keys. So if you want to answer this question, we are listed the super keys that are not keys. They are ABC, ABD, BCD, and ABCD. And ABCD. Now, we already answered this question. From these questions, we know if we want to find keys, we can compute the all possible combination of these attributes, the closure of all possible combination of these attributes, so that we can find the attributes whose closure is the set of all attributes. Then it must be a super key, and if it's minimal, then it is the key. And in fact, if we want to find all the keys, we need. It's not necessary to compute all the attributes, all the combination. Let's look at these FDs. AB functional determine C, C functional determine D, and D functional determine A. Check the right side of each FD, C, D, A. We cannot find B. Then, if there is a closure, a set of attributes, if we want to compute the closure of this set, the base is the attribute, and then we'll add the right side, and because no B in the right side, so B must in the base. It must be in the base. So if we want, then it means if we want the closure is ABCD. B must be in the base. Must be in the base. So then we can check the combination, check the combination including B. If the closure is the set of the closure of the set is ABCD. Now, if we compute the closure of B, we know the closure of B is B. So B is not a super key. B is not. But if we add one attribute, for example, AB, we can find the closure of AB is ABCD. And we can find the BC. The closure of BC is ABCD. And the closure of BD is also the ABCD. So if we want to find, in this example, if we want to find all the keys, we just need, we just, we just need compute the combination of set including B. Okay, this is an easier way to find the keys. If you cannot find use this way, you can compute all the combination. Okay, this is the example, and I hope from the discussion of definition of these closure keys and super keys, you can know how what is functional dependencies, and how to find functional assert how to assert functional dependencies based on from database requirement, and how to find keys and super keys for a relation.